Let's address exercise 2.3.19. If T maps R2 into R3 is defined as the following linear transformation, T of x1, x2, as is given by the formula here, and T prime is the second linear transformation mapping R3 into R2, and is defined by this formula here, then we're asked to find a standard matrix representation for the linear transformation that's T prime composed with T. The domain of T is R2, the codomain of T is R3, the domain of T prime is R3, the codomain is R2. So we'll have, when we take the composition, a mapping that goes from R2 through R3 back to R2. And in addition, we're asked to find a formula for T prime composed with T. For the standard matrix representation, let's look at the notes from section 2.3. Corollary 2.3a tells us how to find the standard matrix representation of any linear transformation, and it's simply a matter of applying the transformation to each of the standard basis vectors for the domain of the linear transformation. Okay, so we'll do that. We'll find standard matrix representations for both of these transformations, and then we'll use that to find a standard matrix representation for the composition. Okay, so that was what? Corollary 2.3.a by corollary 2.3.a. We apply T and T prime to the standard basis elements of their respective domains. So consider, okay, transformation T has domain R2, so we'll apply T to the I and j vectors. We'll apply T to the vector 1, 0. Okay, applying T to 1, 0, given the formula here, so we got an input x sub 1 is 1, an input x sub 2 is 0, will give us 2, 1, 1 as output. And if we'll apply T to the vector 0, 1, similarly, input now as x1 is 0, x2 is 1, we'll get 1, 0, negative 1. 1, 0, negative 1. This will give us the, as it said in the corollary, this will give us the columns of the matrix that represents transformation T. And we also need a matrix that represents transformation T prime. So next, consider the T prime transformation applied to, okay, T prime has as its domain R3. Domain is R3, so we'll apply it to the I, j, and k vectors, the standard basis vectors for R3. So 1, 0, 0. Okay, x1 is 1, so we'll get out 1, comma 1. The remainders are zeros, 1, comma 1. We'll apply T to 0, 1, 0. All right, 0, 1, 0 will give us out negative 1, 1. And we'll apply T prime, that is, to the k vector 0, 0, 1. Okay, x3 is 1, so we'll get a 1 out for the first component and a 0 out for the second one. So, by corollary 2.3.a, the standard matrix representations are The book's notation is to use A to represent transformation T and A prime to represent transformation T prime, so we'll follow that notation. We'll take the basis vectors, the images of the basis vectors under transformation T. So the vector 1, 0 is mapped to the vector 2, 1, 1. That will become the column of the standard matrix representation. First standard basis vector, first column. Second standard basis vector, second column. 1, 0, negative, excuse me, negative 1. And for the other transformation, A prime, we've got I, J, and K, and their image is produced as columns 1, 1, negative 1, 1, and 1, 0. So there's the standard matrix representations of T and T prime. But we weren't asked for the standard matrix representations of T and T prime. We were asked for the standard matrix representation of the composition. So let's run to the notes and find the relevant result for standard matrix representations of a composition. That's also in this section. Here we go. Theorem 2.3.b says when composing transformations, multiply standard matrix representations. So this is actually the same order and the same notation in this example. So the standard matrix representing the composition will be the matrix product A prime A. Okay, that was theorem 2.3.b by theorem 2.3.b, the standard matrix representation of the composition T prime composed with T is the product in the same order, matrix A prime times matrix A. Okay, and by the way, we're getting a standard matrix representation of a mapping from R2 to R2. So we better have a 2 by 2 matrix when we're done. A prime is, let's see, in terms of rows, 1, negative 1, 1, and 1, 1, 0. A in terms of rows is 2, 1, 1, 0, 1, negative 1. Okay, so we'll do our row times column thing, and we'll get 2 minus 1 plus 1. First row, first column. First row, second column. 1, 0, negative 1. 1, 0, negative 1, 0 there. Second row, first column, 2 plus 1 is 3. Second row, second column, 1 plus 0 plus 0. There you go. There's a standard matrix representation for a composition. And it's indeed a 2 by 2 matrix. So at least we got that part right. Now they also ask us for a formula for the composition, and all we have to do for that is apply the composition to a vector of the form x1, x2. So let me get a little room for that. And since we have a standard matrix representation for the transformation, piece of cake, it'll just be a matrix product. Okay, so the formula for the composition T prime composed with T is given by T prime composed with t of x1, x2. Well, we know that's represented by the matrix product times the x vector, if you like. The matrix is given here, 2, 0, 3, 1 in terms of rows, and we'll have to write the vector as a column vector. Okay, and we do our product thing, first row, first column, gives us 2x1, 2x1. Second row, first column, gives us a 3x1 plus x2. There's a formula. They gave us formulas in terms of row vectors, so let's give our answer in terms of row vectors. So we could write t prime composed with t of x1, x2 is the vector with components 2x1, 3x1 plus x2. And there's the answer to the second part. There's a formula for the composition of the two functions.